One challenge is what happens when multiple CPUs reference the same data, X in this case. The data could appear in multiple caches. Or in this case, when we have multiple memory modules, X is actually present in one of the memory modules, but both of the CPUs referenced it, and so it appears in both of their caches. On some architectures, this is a problem that has to be dealt with purely in software. Otherwise, the caches will be not coherent. For instance, if on one CPU we update X to be 3, the hardware is not going to do anything about the fact that the value of X in the cache of another CPU is 4. This will have to be fixed in software. These are called non-cache coherent architectures. On other platforms, however, the hardware will take care of all of the necessary steps to make sure that the caches are coherent. So when one CPU updates X to be 3, the hardware will make sure that the cache on the other CPU is also updated. These are called cache coherent platforms. The basic methods that are used in managing the cache coherence are called write invalidate and write update. Let's see what happens with each of these methods when we have a situation where a certain value is present in all of the caches on these two different platforms. In the write invalidate case, if one CPU changes the value of X, then the hardware will make sure that if any other cache has cached that particular variable X, that value will be invalidated. Future references on this CPU to that same value X will result in a cache miss and will be pushed over to memory. The memory location clearly has to be updated based on one of the methods, write through or write back. In the write update case, when one CPU changes the value of X to X prime, then the hardware makes sure that if any other cache has cached that same memory location, its value gets updated as well, as the name of this method suggests. Subsequent accesses to this memory location from the other CPU will result in a cache hit and will return the correctly updated new value. The trade-off is that with write invalidate, we actually pose lower bandwidth requirements on the shared interconnect in the system. This is because we don't actually have to send the full value of X, just its address so that it can be invalidated on other caches. Plus, once a cache line is invalidated, future modifications to the same memory location will not result in subsequent invalidations. That location is already invalidated. So if the data isn't needed on any of the other CPUs anytime soon, it is possible to amortize the cost of the coherence traffic over multiple changes. So basically, X will change multiple times over here before it's needed on the other CPU, and it's only going to be invalidated once. That's what we mean by this amortized cost. For write update architectures, the benefit is that the data will be available immediately on the other CPUs that need to access it. We will not have to pay the cost to perform another memory access in order to retrieve the latest value of X. So then clearly programs that will need to access the value of X immediately after it has been updated on another CPU will benefit from support for write update. Note that you as a programmer, you don't really have a choice in whether you will use write update or write invalidate. This is a property of the hardware architecture, and whichever policy the hardware uses, you will be stuck with it.